The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let's talk about the historical arcs of vision and auditory sciences. In the mid-20th century, auditory psychophysics was like a pretty robust and diverse field, but currently there are very few auditory faculty in psychology departments, whereas like vision faculty are cornerstone of basically every psychology department in the country. In a similar vein, automated speech recognition is this big, fruitful field, but there's not much kind of broader automated sound recognition. In contrast, computer vision is this huge field. So I'm just kind of wondering, historically and sociologically, how did we get here?
You probably thought about this more than most.
Sure, yeah. Yeah, I'm happy to tell you my take on this. Yeah, so it's I think they're really interesting case studies in the history of science. I mean, if you go back to the 50s, psychoacoustics was sort of a centerpiece of psychology. I mean, if you looked around at like the top universities, they all had really good people studying hearing, and even like some of the names that like Green and Sweats, the guys that invented signal detection theory, pretty much, they were psychoacousticians. People often forget that, but they sort of literally wrote the book on signal detection theory. When
people talked about separating the signal from the noise, they meant actual noise.
Yeah, and there was this famous psychoacoustics lab at Harvard that everybody kind of passed through. And so back then, I mean, what constituted psychology was something like pretty different, and it was really kind of closely related to things like signal detection theory. It was pretty low level by the standards of today. And what happened over time is that hearing kind of gradually drifted out of psychology departments, and vision became more and more prominent. I think the reason for this is that there's one really important, there are several forces here, but one really important factor is that hearing impairment is something that really involves abnormal functioning at the level of the cochlea. So the actual signal processing that's being done at the cochlea really changes when people start to lose their hearing. And so there's always been pretty strong impetus coming in part from like the NIH to try to understand hearing impairment and to know how to treat that. And knowing what happens at the front end of the auditory system really has been critical to making that work. In contrast, I mean, most vision impairments they're optical in nature, and you fix them with glasses, right? So it's not like studying vision is really going to help you understand visual impairment. And so there was never really that same thing. And so, whereas when psychology sort of gradually got more and more cognitive, vision science went along with it. That really didn't happen with hearing, and I think part of that was the clinical impetus to try to continue to understand the periphery. The auditory periphery was also just harder to work out because it's a mechanical device, the cochlea, and so you can't just stick an electrode into it and characterize it. It's actually really technically challenging to work out what's happening, and so that just kept people busy for a very long time. But as psychology was sort of advancing, what people in hearing science were studying kind of ceased to really be what psychologists found interesting, and so the field kind of dropped out of psychology departments. It moved into speech and hearing science departments, which were typically at bigger state schools, and they never really got on the cognitive bandwagon in the same way that everybody in vision did. And then what ends up happening in science is there's this interesting phenomenon where people get trained in fields where there are already lots of scientists. So if you're a grad student, like, you need an advisor, and so you often end up working on something that your advisor does. And so if there's some field that is underrepresented, it typically gets more underrepresented as time goes on. And so that's sort of been the case. If you want to study olfaction, it's a great idea, right? But like, how are you going to do it, right? You got to find somebody to work with. There's not many places you can go to get trained, and the same has been true for hearing for a long time. So that's my take on that part of it.
Yeah, Hynek, do you have anything to say on the computational?
No, I don't know. I'm thinking if it is something also about the tools available, because in the old days it was easier to generate the sounds than to generate images like on a computer. Now it's much easier, right? So vision and visual research became sexier. It's also, I teach auditory perception to engineers. Also, I teach a little bit of visual perception, and I noticed that they are much more interested in visual perception, especially the various effects, and you know, because somehow you can see it better. And the other thing is, of course, funding. I mean, you know, this the hearing research is main applications are, as you said, hearing prosthesis. These people don't have much money, right? In speech recognition, we didn't get much of the benefits yet from hearing research, unfortunately. So I wonder if this is not also a little bit
Can I add one?
to do with it.
So maybe this is sort of things you guys also gestured towards, but I think in both, and to go back towards similarities and not just differences, maybe that's what I'll be my theme. In both vision and hearing or audition, there's, I think, a strong bias towards the aspects of the problem that fit with the rest of cognition, and often that's mediated by language, right? So there's been a lot of interest in vision on object recognition, parts of vision that ultimately lead into something like attaching a word to a part of an image or a scene. And there's a lot of other parts of vision, like certain kinds of scene understanding, that have been way understudied until recently also, right? And it does seem like the parts of hearing that have been the focus are speech. I mean, there are lots of people in, it's maybe not as much as vision or object recognition, but certainly there's a lot of mainline cognitive psychology who studied things like, you know, categorization of basic speech elements and things that just start to bleed very quickly into psycholinguistics, right? Whereas the parts of hearing, at least that's been where a lot of the focus, but the parts of hearing that are more about auditory scene analysis in general, like sound textures or physical events or all the richness of the world that we might get through sound, has been super understudied, right? But echoing something Josh said also, or implicitly, is just because it might be understudied and you need to find an advisor doesn't mean you shouldn't work on it. So if you have any interest in this, you know, and there's even one person, say, who's doing some good work on it, you should work with them. And it's a great opportunity.
And I can follow that up and just say that, I mean, my sense of this is, if you can bear with it and figure out a way to make it work, in the long run, it's actually a great place to be. You know, it's a lot of fun to work in an area that's not crowded.
Yeah. Cool. All right. Another, like, obviously a large, to kind of transition, like a large emphasis of the summer school is on potential symbiosis between like machine and like engineering and science. And so I guess like what have been the most kind of fruitful interactions between machine perception, either vision or hearing, over the years, and are there any kind of lessons that we can learn in general?
You know, I went a little bit backwards, quite frankly. I'm trained as an engineer, and I was paid always to build better machines. And in the process of building better machines, we discovered that almost unknowingly we were emulating some properties of hearing. So then I, of course, started to be interested, and I wanted to get more of it. So that's how I got into that. But I have to admit that in my field, we are a little bit looked down at. Because, well, mainly not all that much, because engineers are such that the crowd that if something works, they like it, and they don't much want to know why, you know, or at least they don't talk much about it. So it's interesting when I'm in engineering meetings, they look at me as this strange kid who works also on hearing. When I'm in an environment like this, people look at me like a speech engineer, but I mean, I don't even feel either in some ways. But what I was wondering when Josh was talking about, is there anybody in this world who works on both? Because, you know, that I think is much more needed than anything else. I mean, somebody who is interested in both audio and visual processing and is capable of making so
not both science and engineering, but both vision and audition.
Yes, that's what I mean, vision and audition, with a real goal, trying to understand both and trying to find the similarities. Because personally, I got some inspiration from visual research. Even in work when I work with audio, but I don't see much of it anymore. And there are some basic questions which I would like to ask, and maybe I should have sent it in, which is like, I don't even know which modes are the similar and different in audio and vision. Should I look at time? Should I look at modulations? Should I look at the frequencies? Should I look at the spatial resolution? And so on and so on. So I don't know if somebody can help me with this. I would be very happy to go home and knowing that. I mean, sometimes I suspect that spatial resolution and frequency resolution in hearing are similar. I'm thinking about modulations in speech. Josh talked a lot about it, but there must be a modulations in vision also. But of course, we never studied much of the vision of the moving pictures. A lot of vision research was fixed, basically the images, right? It was a little bit like in speech, we used to study steady vowels. We don't do it anymore because the real speech is something very, very different. The same thing is in image processing. I think that now it's getting more and more because, again, I mean, I'm going back to availability of the machines. You can do some work on moving images and on video and so on and so on. But I don't know how much of that is happening. And so my question is really, are there any similarities and on which level they are? I mean, sort of there is a time, there is a spatial frequency, there is a carrier frequency, there are modulations in speech. I don't know. I mean, I would like to know this. I mean, that's something, if somebody can help me.
Oh, well, I had something. I think those are interesting questions, but I'm sure I don't have the answers at this point. But I was going to say something a little, going back to the original general question, which is, again, sort of thinking about it from a historical point of view, I think is helpful. In the long run, I think what's happened over the past 50 years is that biological inspiration has been very helpful at injecting ideas into the engineering realm that end up being very powerful, right? I mean, I think we're seeing kind of the arc of that right now in a very strong way. I mean, in terms of vision and audition, the sort of algorithms that are most dominant are ones that were strongly biologically inspired. And there had been a historical arc over, I think, a period of decades where first the algorithms were sort of biologically inspired back in the 50s and 60s, and then they were not biologically inspired for a while. Like the biology stuff didn't seem to be panning out. That was sort of the dark ages of kind of neural networks, and then more recently that has begun to change. And again, biologically inspired ideas seem to be very powerful from creating for creating algorithmic approaches. But the arc is a very long one, right? And so it's not like you discover something in the lab and then like the next day you would go implement it in your algorithm and suddenly you get 20% improvement on some task, right? That's not realistic. Okay, but if you're willing to have the patience to wait for a while and like sort of see ideas sort of slowly percolate up, I think they can be very powerful. Now, the other direction is really also very interesting, like using the algorithms to understand neuroscience, right? That's one where like you can get a lot of bang for your buck quickly, right? And it's sort of like that's a short-term sort of high, right? Because what happens is that like you take this machine that you didn't understand and you apply it to this problem that you were worried about and that is sort of scientifically interesting, and suddenly you get 20% improvement overnight, right? That is feasible in that direction, e.g. taking advances from the computational side or in the algorithmic side and applying them to understanding data and neuroscience. That does seem to have been borne out, but only much more recently. So there wasn't much of that at all for many decades, but more recently that has begun to happen. And so I think that there is a really interesting open question right now as to which direction is more live, which one is leading at this point, I think is a really interesting question. Maybe neither of them is leading, but I think that certainly from on the everyday, on the ground experience as somebody who's trying to do some of both, it feels like the algorithms are leading the biology, okay, or leading the neuroscience to me, in the sense that I feel like in the short run, at least, things are gonna come out of the community of people doing algorithms development that are gonna help understand neuroscience data before specific things are gonna come out of the neuroscience community that are gonna help make better algorithms, like in the short run. Okay, again, I think the long run can be different, and I think that's a really deep, open, like research program question, is which tasks are the ones that you should choose such that learning about them from a neuroscience and psychology point of view will help in the 5 to 10 year run make better algorithms. And if you can choose those correctly, I think you really have done something valuable, but I think that's really hard. So
yeah, I want to push back. I like how you said how the engineering is really helping the science right now, but the science, the seed that the science planted in the engineering, like what you're talking about is just CNNs basically.
Oh, well, I think not entirely, because I think that there are some ideas in recurrent neural networks too.
Okay, sure, yeah. Neural networks generally, yeah. But like the point is like the ideas that were kind of inspired from that have been around for decades and decades and decades. Are there other kinds of key examples besides the operations that you throw into a CNN, and the idea of convolution, and the idea of layered computation? These are obviously very, very important ideas, but what are kind of other contributions that science has given engineering besides those?
Well, Green and Sweat, even just, I mean, the thing that he mentioned earlier about Green and Sweats is another great example.
Yeah.
Right. Psychophysics helped understand signal detection theory. But that's much older. But that's a very clear example.
Signal detection theory didn't come from Green and Sweats. It came from Second World War.
I was just thinking of all the work.
Yeah, they did a very good work, obviously, and they indeed were auditory.
Right, and they were doing a lot of work during government.
They formalized all this stuff.
Right? Yeah, and they did a lot. Actually, it's interesting. But it's interesting. There's this great paper that Green and Sweats have where they talked about their military work. Right, and they actually worked for the military, just determining which type of plane was the one that they were going to be facing. And so, I agree, it came out of that.
Yeah. If I can still spend a little bit of time on engineering versus science, we also are missing one big thing, which is like Bell Labs. Bell Labs was the organization which paid people for having fun, doing really good research. And there was no question that at the time Bell Labs were about speech and about audio. So there was a lot of things were justified, and even Bell US and these people, they pretended they are working on perception because the company wanted to make more money on the telephone calls. This is gone, right? Both. Speech is gone, Bell Labs is gone, and maybe image processing is in, because the government is interested in finding various things from the images and so on and so on. So it's a lot of that is funding. And since you mentioned neural networks, it never stops amazing me that people would call artificial neural networks anything similar to biology. I mean, the only thing which I see similar there maybe are now these layered networks and that sort of thing.
I think a lot of the concepts were inspired by that. I don't think it was directly, I don't think anyone takes it as a super serious.
But there I still have maybe one point to make. Most of the ideas which are now being explored in the neural networks are also very old. The only thing is that we didn't have the hardware, we didn't have the means, basically, of doing so. So technology really supported this, and suddenly, it's working, but to some people it's not even surprising that it's working. They say, of course, except we couldn't do it.
I think what was surprising to them was that it didn't work for so long. Yeah, and that, that people were very disappointed and upset about that, and then, but I agree that basically there's all these, all the ideas are these 40-year-old or 50-year-old ideas that people had thought of, typically many of them coming out of the psychology and neuroscience community a long time ago, but just couldn't do anything about it. And so that takes a long time to bear fruit, it feels like.
So I have more questions rather than answers, but to try to get back to the question about vision and hearing and how we can synergistically interact between the two. First, I wanted to lay out a couple of biases and almost religious beliefs I have on the notion that cortex is cortex, meaning that there's a 6-layer structure, that there are some patterns of connectivity that have been described both in the vision, in visual cortex as well as auditory cortex, that are remarkably similar, and we have to work with the same type of hardware in both cases. The type of plasticity, learning rules that have been described are very similar in both cases, so there's a huge amount of similarity at the biological level. We use a lot of the same vocabulary in terms of describing problems about invariance and so on. And yet at the same time, I wanted to raise a few questions, particularly to demonstrate my ignorance in terms of the auditory world and get answers from these two experts here. I cannot help but feel that maybe there's a nasty possibility that there are differences between the two. In particular, the role of timing has been somewhat underexplored in the visual domain. We have done some work on this, some other people have, but it seems that timing plays a much more fundamental role in the auditory domain. Perhaps the most extreme example is sound localization, where we need to take into account microsecond differences in the arrival of signals between the two ears. I don't know anything even close to that in the visual domain. So that's one example where I think we have to say that there is a fundamental difference. Now, thinking more about sort of the kind of recognition questions that many of us are interested in, I think again, timing seems to play a fundamental role in the auditory domain. But I would love to hear it from these two experts here. I easily come up with questions about what is an object in the auditory domain that's sort of defined in a somewhat heuristic way in the visual domain, but we all sort of agree on what objects are, and I don't know what the equivalent is in the auditory domain, and how much attention should we pay to the fact that the temporal evolution of signals is a fundamental aspect in the auditory world, which we don't really, by and large, we don't really think about too much in the visual domain. With that said, I do hope that at the end we will find similar fundamental principles and algorithms because, as I said, cortex is cortex. But
well, I can speak to some of those issues a little bit. I mean, look, I think it can be. I mean, it's an interesting and fun and I think often useful exercise to try to map kind of concepts in one modality onto another. But again, at the end of the day, right, the purpose of perception is just to figure out what's out there in the world. And the information that you get from different modalities, I think in some cases, it just tells you about different kinds of things. I mean, and so sound is usually created when something happens, right? Which, and it's not quite the same thing as there being an object there, right, off of which light reflects. I mean, sometimes there's some sense in which there's an object there, like a person, right? A person's producing sound. But oftentimes the sound is produced by an interaction between a couple different things. And so really the question is sort of what happened as much as what's there. And so, you could probably try to find things that are analogous to objects, but it's, in my mind, it may just not be exactly the right question to be asking about the sense.
Can I just comment on that one?
Sure.
Which is, yeah, I mean, I think, again, this is a place where Gabriel and I have somewhat different biases, although, again, it's all open. But that an object to me is not a visual thing or an auditory thing. An object is a physical thing, right? So those of you who saw Liz Spelke's lectures on this is very inspiring to me that from very early on, infants have a concept of an object, which is basically a thing in the world that can move on its own or be moved. And the same principles apply in vision, but also haptics. And it's true that the main way we perceive objects is not through audition, but we can certainly perceive things about objects from sound, and often just echoing what Josh said, it's the events or the interactions between objects that make sounds. They make the physically cause sounds, and so it's often what we're learning from sound is. But
maybe if I could ask, reformulate. I don't disagree with your definition of objects,
right.
A la Spelk and so on. So, but I guess in the auditory domain, if I think about speech. I mean, are we talking about phonemes? Are we talking about words? I mean, if we talk about Lady Gaga or Vivaldi, are we talking about a whole piece of music, a measure, a tone, a frequency? These are things that.
So structure.
And what is it?
Structure more generally.
What's the unit of computation that we should think about algorithmically in the same way that Dan and us and many others think about algorithms that will eventually have labels on objects, for example.
I mean,
what are those fundamental units? And maybe the answer is all of them.
Well, speech is really interesting, right? Because from one point of view, you could think of it as like it's basically like it's an artifact, right? Speech is a thing that's created through biological and cultural evolution, manipulating a system to kind of create these artificial event categories, which we can call phonemes and words and sentences and so on. And surely there was audition before there was speech, right? So it seems like it's building on a system that's going to detect a more basic notion of events, physical interactions, or things like babbling brooks or fires or breezes, and then animal communication that hacks that basically, both on the production side and the perception side. So it's very interesting to ask what's the structure, what's the right way to describe the structure in speech. It's probably seems most analogous to something like gesture. That's a way to hack the visual system to create these events visually, salient changes in motion, whether for just nonverbal communication or something in sign language. It's super interesting, right? But I would say the analog speech isn't a set of objects, it's a set of structured events which have been created to be perceivable by a system which was evolutionarily much more ancient one, perceiving object interactions and events.
But I mean, I also think it's the case that, there's a lot of focus on objects in vision, but it's certainly the case that vision is richer than just being about objects, right? I mean, there are, right? I mean, it's just, I think in some sense the fact that you are posing the question, it's a reflection of where a lot of work has been concentrated on. yeah, there's obviously, you have scenes, there's stuff, not just things, right? And the same is true in Audition, and the difference is just that there isn't really as much of a focus on like things, often because those are not.
I agree. I guess the fundamental question I'm trying to raise, as well as the question about time, in the visual domain, let's get away from objects and think about action recognition, for example. And that's one domain where you would think that, well, you have to start thinking about time. It's actually extremely challenging to come up with good stimuli that you cannot recognize, where you cannot infer actions from single frames. And I would argue, but please,
let's talk about events.
But let me say one more thing, and then but please correct me if I'm wrong. I would argue that in the auditory domain, it's the opposite. It's very hard to come up with things that you can recognize from single instances. You need time. Time is inherent to the basic definition of everything. In the visual domain, again, we've thought about time and what happens if you present parts of objects asynchronously, for example, and you can disrupt object recognition or action recognition in that way. But it's sort of a minor. Again, you can do a lot without time or without thinking too seriously about time. Then maybe, I don't know, time is probably not one of your main preoccupations, I suspect, in the visual domain.
I'm not sure, because one of the big things which always strikes me in vision is the saccades, and the fact that we are moving eyes, and the fact that it's possible even to lose the vision basically if you really fix the things on the retina and so on and so on. So vision probably figured out different ways of introducing time into perception, basically moving eyes, and maybe it sounds, yeah, indeed is happening more like already out there. But I had one joint project actually where we tried to work audiovisual recognition, and it was a project about recognizing unexpected things. And there was a big pain initially because, of course, vision people sing in one way, auditory people sing in another way. But eventually we ended up with the time and with the surprises and with the unexpected and with the priors. And there's been a lot of similarities between audio and visual world. So that's why I was maybe saying at the beginning, people should be more encouraged. Now I'm looking at the students to look at both. I mean, don't just say I'm a visual person and I just want to know a little bit about speech or something. No, I mean, these things are very interesting. And of course, I mean, in auditory world, there are problems which are very similar to visual problems, and in visual world, there are very similar problems to auditory work. I mean, you just take a speech and take a writing, right? And be it handwriting or be it even printed things. I mean, these things communicate messages, communicate information in a very similar way. So I would just say, I got a little bit excited because I finished my coffee, but I would just say, let's look for the similarities rather than differences. Yeah. And let's be very serious about it. Like sort of say, oh, finally I found something. Like, for instance, I give you one little example. We had a big problem with the perceptual constancy when you get the linear distortions in the signal. And I just accidentally read some paper by David Marr at the time, and I didn't understand it. I have to say I actually misinterpreted it a little bit, but still it was a great inspiration. And I came up with an algorithm which ended up to be a very good one. Well, at the time, I mean, now it's been beaten many times, but let's just look for the similarities. That's what I'm somehow maybe arguing, and that was also my quest. Like, sort of, I don't even know what is similar and different in auditory and visual signals. So, certainly, maybe on certain level, it must be the same, right? The cortex is very, very similar. So I believe that indeed, I mean, at the end, we are getting information into brain, which is being used for figuring out what's happening in the world. But, and there are these big differences at the beginning. I mean, the sensors are different.
Could I nominate one sort of thing that could be very interesting to study, that's very basic in both vision and audition, where there's some analogies, which is certain kinds of basic events that involve physical interaction between objects. Like, I'll try to make one right here. Right, okay. So there was a visual event, and it has a low-level signal, a motion signal. There was some motion over here, then there was some other motion that, in a sense, was caused. There was some sound that went with it. There was the sound of the thing sliding on the table, and then the sound of the collision. We have all sorts of other things like that, right? Like, I can drop this object here, and it makes a certain sound. And so there's very salient, low-levelly detectable both auditory and visual signals that have a common cause in the world, one thing hitting another. It's also the kind of thing which, I don't know if Liz mentioned this in her lecture, I mentioned this a little bit, even very young infants, even 2-month-olds understand something about this contact causality, that one object can cause another object to move. It's the sort of thing that Shimon, right, has shown, Shimon-Ullman has shown. You can, in a very basic way, use this to pick out primitive agents like hands as movers. So this is one basic kind of event that has interesting, I think, parallels between vision and audition, because there's a basic thing happening in the world, an exertion of force between one moving object when it comes into contact with another thing, and it creates some simultaneously detectable events with analogous kinds of structure. I think a very basic question is, you know, if we were to look at the cortical representation of a visual collision event and the auditory side of that, you know, how do those work together? What are similarities or differences in the representation and computation of those kind of very basic events?
If I may, if I still may, obvious thing to use is use vision to transcribe the human communication by speech. If somebody wants a lot of money from Amazon or Microsoft or Google or government, you know, work on that, because there is a clear visual channel which is being used very heavily. You know, not only that, I move the hands and that sort of things. If somebody can help there, I mean, that would be great. And it's actually a relatively straightforward problem. I'm not saying simple, but it's well defined. Basically, there is a message which is being conveyed in a communication by speech, and it's being used. I mean, lips are definitely moving unless you are working with a machine, and hands are moving unless you are a really calm person, which none of us is. And so this is one direction.
Basic speech communication.
Basic speech communication is multimodal thing. That would be great, really.
I mean, it's also worth saying, I think, you know, most of perception is multimodal, right? I mean, you can certainly come up with these cases where, you know, you rely on sound and have basically no information from vision and vice versa, right? But I mean, most of the time, you get both, and you don't even really think about the fact that you have two modalities. You know, you're just, you know, you want to know what to grab or whether to run or, you know, whether it's safe to cross the street, and, you know.
Of course, the thing is that you can switch off one modality without much damage. That's okay, because that's in most of the perception, this is always the case. You don't need all the channels of communication. You only need some. But if you want to have a perfect communication, then you would like to use it. I mean, sort of, but I absolutely agree with this. Sort of, the world is audiovisual.
This was a comment I was going to add to our discussion list, right, which I shared with Alex, but maybe not the rest, is I think it's a really interesting question. What can be understood about the similarities and differences in each of these perceptual modalities by studying multimodal perception? And to put out a kind of a bold hypothesis, I think that for reasons that you guys were just saying, because natural perception is inherently multimodal, and it's not just these ones, it also involves touch and so on, I think that's going to impose strong constraints on the representations and computations in both how vision and audition work. The fact that they have to be able to interface with a common system, what, you know, I would think of it as a kind of physical object event system, but however you want to describe it, the fact of multimodal perception's pervasiveness, the fact that you can switch on or off sense modalities and still do something, but that you can really just so fluently, naturally bring them together into a shared understanding of the world, that's something we can't ignore, I would say.
Why are people so sure that during everyday life most things are multimodal? I'm not even sure how to quantify that, but is there any quantification of these?
No, I don't know of a quantification. All I mean is that you're, you know, most of the time, right? I mean, you're listening and you're looking and you're doing everything you can to figure out what happened, right? I mean, it's like, you know, you want to know if there's traffic coming, right? I mean, there's noise that the cars make. You also look, you know, you do both of those, and you probably don't even really think about which of them you're doing.
I'm not sure about the most of the time part. Yes, that's a very good example, I think, of multimodal experience. I can cite lots of other examples where I'm running and listening to music, and they're completely decoupled, or I'm working on my computer.
You don't listen to music when you're driving, right?
I do, but
No, but I mean, not in the way that, like, I mean, sure, you listen to music, okay, obviously, right. We listen to music when we're driving, but we try it, it's sort of important that it doesn't drown out all other sounds.
I'm just
maybe,
wondering
maybe not, I guess,
to what extent
okay,
this,
fine.
I don't even know. But,
and how much of that is like kind of the particular, like like in the contemporary world, you can actually decorrelate these things in a way that in the natural world you can't. Yeah. Like if you were a monkey, these things would probably be a lot more correlated than you are as a human in the 21st century. Like there would be a common physical world causing both the input to both your modalities in a way that you can break now, right? Like that, I don't know, that feels...
You may be right. I haven't really thought deeply about this.
No, it would be interesting to give.
I'm not really sure,
to give you some statistics of this. I mean,
I'm not disputing the usefulness of multimodal perception. I think it's fantastic. I'm just wondering. I think vision can do very well without the auditory world, and vice versa.
We could just close our eyes right now, all of us, and we'd have a fine panel for a while. But I mean,
yeah.
But many of the social dynamics would be invisible. Literally, and
no, I think you probably get a lot from prosody.
It's an open question.
You get some, but there's a difference. Have you ever listened to a radio talk show? Sometimes these days the shows are broadcast on TV, and it's like when you watch, you're like, oh my, you have a totally different view of what's going on, or like if you're there in the studio. I mean, I totally agree that these are all open questions, and it would be nice to actually quantify. For example, what to me is this often subjective experience, like if sometimes if the sound is, I don't know, you turn off the sound in something where you're used to having the sound, it changes your experience, right? Or you turn on the sound in a way that you had previously watched something, right? Like you could do experiments where you show people a movie without the sound, and then you turn on the sound, and it's gonna, in some ways transform what they see, in some ways not. So maybe the right thing to say more data is needed, but
don't you guys think though that even independent of multimodal, there's still actually a lot of even more basic questions to be asked about similarity and differences? Like, I mean, just from my point of view, since that's the only one I'm easily able to take, like you took a bunch of convolutional neural networks and you trained some of them on vision tasks and some of them on audition tasks, right? And you figured out which architectures are good for audition tasks and which are good for vision tasks. See if the architectures are the same, and if indeed the architectures are fairly similar, then like looking at the differences between the features at different levels. I mean, I know that that's a very narrow way to interpret the question, but it's one, and there's probably a lot that can be...
So you guys have been doing that. What have you learned from doing that?
We haven't done it that exhaustively.
We haven't done it that exhaustively, yeah. but suffice it to say that the hints are, I think, very interesting. Yeah. Like, you begin to see like places where there are clear similarities and clear differences, and asking like, where do the divergences occur? Are there any like underlying principles about like what layers or what levels in the model those divergences start to occur? Can you see similarities at all layers, or do you start to see sort of like a kind of a clear branching point? Right. Moreover, like what about lower layers, right? I mean, you actually see differences in sort of frequency content in auditory data, and in differences between that and in visual data that seem to emerge very naturally from the underlying similarities, underlying differences between the statistics. But still, downstream from there are some deep similarities about extraction of objects and of some kind or other, auditory objects potentially. And so I think that that's a very narrow way of posing the question, and I don't say that everybody should pose it that way by any means. But I just think that before we get to multimodal interaction, which is interesting, I think there's just this huge space of like clear, very concrete ways to ask the question of similarities and differences that are like almost no matter what you'll find something interesting.
You're saying if we enlarge the discussion from just talking about vision audition to other parts of cognition, then we'll see more of the similarities between these sense modalities, because they will be the differences that stand out in relief with respect to the rest of cognition. Yeah, I mean, I think that's a valuable thing to do, and it connects to what these guys were saying, which is that there's a sense in which this, something like these deep convolutional architectures seem like really good ways to do pattern recognition, right? This is what I would see as the common theme between where a lot of the success has happened in vision and audition. And I don't think, and it's again, everybody here has heard me say this a bunch of times, I think that pattern recognition does not exhaust by any means intelligence or even perception. Like I think even within vision and audition, there's a lot we do that goes beyond, at least on the surface, pattern recognition and classification. It's something more like building a generative model. Maybe this is a good time that's another theme you wanted to bring in, but something about building a rich model of the world and its physical interactions. And to me, there's this, and again, something Dan and we've talked a lot about, and I think it's, you've heard some of this from me, and Dan has got some really awesome work in a similar vein of trying to understand how basically deep pattern recognizers, maybe that's another way we could call it, deep convolutional pattern or just deep invariant pattern recognizers, where the invariance is over space or time windows or whatever it is that deep convolutional networks are doing. These are obviously important tools. They obviously have some connection to not just the 6-layer cortex architecture, but these multiple, the things that goes on in the ventral stream, for example, or I don't know, the auditory system as well, but it's going on from one cortical area to the next, a hierarchy of processing. That seems to be a way that cortex has been arranged in these two sense modalities in particular to do a really powerful kind of pattern recognition. And then I think there's the question of, okay, how does pattern recognition fit together with model building? And I think in other areas of cognition, you see a similar kind of interchange, right? It might be like this has come up a little bit in action planning, like model-based planning versus more model-free reinforcement learning, and those are, again, a place where there might be two different systems that might interact in some kind of way. I think pattern recognition also is useful all over, where cognition starts to become different from perception. For example, there's so many ways, but things like when you have a goal and you're trying to solve a problem, do something. Pattern recognition is often useful in guiding problem solving, right? But it's not the same as a plan, right? So I don't know if this is starting to answer your question, but I think it's this idea of intelligence more generally as something like, the way Laura put it for learning, same idea. She'd put it as like goal-directed or goal-constrained. How did she put it? Problem solving or something like that, right? That's a good way to. If you need one general-purpose definition of cognition, that's a good way to put it. And then. On the other hand, there's pattern recognition, and so you could ask, well, how does pattern recognition more generally work, and what have we learned about how it works in the cortex or computationally from studying the commonalities between these two sense modalities? And then how does pattern recognition play into a larger system that is basically trying to have goals, build models of the world, use those goals to guide its action plans on those models?
On the topic of convolutional neural networks and deep learning, how they are reaching kind of impressive successes, and they might eliminate some similarities and differences between the modalities. But in both cases, the biological or the learning algorithm is extremely unbiological. And I was wondering if any of you guys, infants don't need millions of examples of labeled data to learn to learn what words are. So I was wondering if you guys have any kind of thoughts on how to make that algorithm more biologically plausible.
I would go to what Josh said earlier, which is you look at those in a real physically embodied environment, you look for those low-level cues that can be used to be a proxy for the higher level information, right? And then what you really want is some way...
be a little more specific? What do you mean?
Well, do you want to be...
So people have heard this from Tommy and others here about sort of kinds of natural supervision, right? Several people have talked about this, right? Is that what you're getting at? The idea that basically often, just tracking things as they move in the world gives you a lot of extra effectively labeled data. These are all, you're getting lots of different views of this microphone now, and I could, or whatever, if we're walking around the stage, or all of our faces as we're rotating. So when you pointed to the biological implausibility of the standard way of training deep networks, I think a lot of people are realizing, and this was the main idea behind Tommy's conversion to now be a strong prophet for deep learning instead of being a critic, right, was that, the issue of needing lots of labeled training, that's not the biggest issue. There's other issues like backpropagation as a mechanism of actually propagating error gradients all the way down to a deep network. I think that troubles more people.
I have quite the opposite view on that.
Okay.
Yeah, I agree that it's true that the specific biological plausibility of a specific deep learning, backpropagation algorithm is probably suspect. But I suspect that by the same token, there are somewhat inexact versions that are biologically plausible, or more plausible anyway, that could work pretty well. I think that's less let me put it this way. I think that's a flashy question. I think if you actually end up solving that both from an algorithmic point of view and maybe more importantly seeing how that's implemented in a kind of real neural circumstance, you end up, you'll win the Nobel Prize. But I think that, I feel like that's something that will happen, right? I think that there's a bigger question out there, which is, I do think that from an algorithmic point of view, which things that people don't yet know how to do, how to replace millions of heavily semantic training examples with those other things, right? The things that you just mentioned a moment ago, the extra data, it hasn't actually been demonstrated how to really do that. And I feel like the details of getting that right will tell us a lot about the signals that babies and others are paying attention to in a way that's really conceptually very interesting. And I think not so obvious at this point how that's I think it'll happen too, but it'll be conceptually interesting when it does in a way that I think that.
Both are pretty interesting.
Yeah.
Some people are more worried about one or the other, but yeah.
Yeah, exactly. And I personally, I would say that from an algorithmic point of view, I'm more interested in that second one because I think that'll be a place where the biology will help us teach how to do better algorithms.
Learning about the biological mechanism of backpropagation seems less likely to transform our algorithms. Although, again, if you ask Andrew Sachs, he's one person, he's been here. He think that's the question he most wants to solve, and he's a very smart person, and I think he has some thoughts on that. But my sympathies are also with you there. I think there are other things besides those that are both biologically and cognitively implausible that need work too. So those are two of the main ones that.
I think you are touching something very interesting, and one of the major problems with machine learning in general, as I see it, which is like use of transcribed or untranscribed data. And I think that this is one direction which actually, specifically in speech, it's a big, big, big problem because, of course, data is expensive. So we know, unless you are Google. But still, even there, you want to have a transcribed data. You want to know what is inside. And clearly, this is not what human beings
You guys have this thing in
using.
speech. I think I'd like to talk more about this because you guys have this thing, particularly at Hopkins, in speech that you call zero resource speech recognition, right?
That's,
and I think this is a version of this idea, but it's one of the places where studying not just neuroscience, but cognition and what young children do, the ability to get so much from so little is a place where we really have a lot to learn on the engineering side from the science.
yes,
right?
I mean, I wish I was involved more, that I could speak about it a little bit more in depth, but definitely this is the direction I'm thinking about, which is like, what do you do if you don't know what is in the signal, but you know there is a structure, and you know that there is something, there is an information in it, and you have to start from the very scratch, sort of figure out where the information is, how is it coded, and then use it in the machine. And I think it's a general problem, or in the same thing is in vision.
Maybe you're asking several different questions. I mean, I don't know if have people in the summer schools talked about these incivility. It's an interesting question. People are very much divided on what they say, and I do think that generative models are going to come out differently there. But again, I don't want to say generative models are better than discriminatively trained pattern recognizers. I think, particularly for perception and a lot of other areas, what we need to understand is how to combine the best of both. So in an audience where people are just, neural networks, rah, 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 and that's all there is, then I'm going to be arguing for the other side. But that's not that I think they are better. I think they have complementary strengths and weaknesses. This might be one. I think pretty much any pattern classifier, whether it's a neural network or something else, will probably be susceptible to these kind of pathologies where you can basically hack up a stimulus that's arbitrarily different from an actual member of the class that gets classified. If you're trying to put a separating surface between two or n finite classes, I was trying to see how to formulate this mathematically. I think you can basically show that it's not specific to neural networks. It should be true for any kind of discriminatively trained pattern classifier. I think generative models have other sorts of illusions and pathologies, but there are definitely going to be my sense is there are going to be some of the ways that any pattern classifier is susceptible that generative models won't be susceptible to, and there will be others that they will be susceptible to. But it's sort of an orthogonal issue. But I think the illusions that generative models are susceptible to are going to generally going to have like interesting rational interpretations. It's going to tell you something. They're less likely to be susceptible to just completely bizarre pathologies that we look at and like, I don't understand why it's seeing that. On the other hand, they're going to have other things that will frustrate us, and my inference algorithm is stuck. I don't understand why it's not, my Markov chain isn't converging. If that's the only way you're going to do inference, you'll be very frustrated by the dynamics of inference, and that's where hopefully some kind of pattern recognition system will come to the rescue. Again, if we just look at anecdotal experience, both in speech and vision, there are certain kinds of cases where, like, in a passing rock, you suddenly see a face, right? Or in noise, or in a tree, people will see Jesus' face on arbitrary parts of the visual world. And also sometimes in sound, you hear something like that. So this idea of seeing signal in noise, that's something I think that's going to be, we know humans do that. But for example, there are ways to get, deep confidence in vision to see, like, you can start off with an arbitrary texture. Have you seen this stuff? And massage it to look like you can start off with a texture of green bars and make it look like a dog and to the network, and it doesn't look like a dog to us. And we're never going to see a dog in a periodic pattern of green and
But
polka
the
dotted
reason
bars.
you can do that is because you have perfect access to the network, right? And if you had perfect
Sure,
access
sure.
to the visual system,
But I'm
you'd
just
be able
saying
to do the
these
exact
don't
same
these
thing,
again.
right?
Well, I don't think so.
Of course,
These
there's
don't.
going to be visual illusions in every case. The question is
Yeah.
whether or not they're going to make sense to humans.
Right, and I
Right.
think some of
And
them.
that's a test of whether or not the
You
model
learn something
is,
from that.
is a
right?
real
And-
model.
And
or
even the,
is a good
just to be
model.
clear, the ones that the convents are susceptible to, that say a generative model or a human isn't, they're not signs that they're fundamentally broken. Rather, they're signs of any discriminatively trained pattern recognizer, I would predict, whether it's good or bad, it's signs of the limitations of pattern recognition.
Or signs of the limitation of the type of tasks that are being used of which the recognition is being done. Like if you replaced something like categorization with something like the ability to capture, like predict geometric and physical interactions X period of time in the future, maybe you'd end up with quite different illusions, right? There's something very brittle about categorization that could lead to the sort of null spaces being very broad.
Exactly, that's what I mean
Right.
by pattern recognition.
Yeah.
I mean pattern classification in particular.
And so
Yes.
I don't think the answer, I don't
Not
think
prediction, but classification.
right, but I don't think it's yet known whether like the existence of these sort of fooling images or these kind of weird illusions, e.g. the models are bad at or do not pick out the correct visual illusions. I don't know whether that, people are not totally sure whether it's like the networks need to have feedback and that'll be what you really need to solve it. It's at that broad level of mechanism. Or is it like the task is wrong? So it's sort of a little bit less bad, or maybe like Josh said, it's like the easiest thing would be, well, actually, if you just did this with the neural system, you'd find exactly the same thing, but we don't have access to it, so we're not finding it, right? And so I think it's not totally clear which of these, where it is yet, right? It's a great question, but I feel like the answers are murky right now.
Yeah. Okay. On the topic of feedback, I wanted to kind of move over, and like Gabriel talked about feedback during his talk, and like there's really heavy kinds of feedback in both these modalities, where like in hearing, as Josh talked about, like it goes all the way back to can alter the mechanics of the cochlea, of the like basilar membrane. That's pretty shocking. That's pretty interesting. So like, what is the role? Like Gabriel talked about a couple of specific examples where feedback would actually be useful. What can we say something more broadly about, in general, when is feedback useful across the two modalities? Do we think there are kind of specific instances? Can we talk about specific instances in each? And
Throughout the visual system, there's feedback essentially all over, except for the retina. Throughout auditory cortex, again, there's feedback and recurrent connections all over. We've been interested in a couple of specific apps where and situations where feedback may be playing a role. These include visual search. These include pattern completion, feature-based attention. I believe, and hopefully Josh will expand on this, that these are problems that, at least at a very superficial level, also exist in the auditory domain, and where it's tempting to think that feedback will also play a role. More generally, you can mathematically demonstrate that any network with feedback can be transformed into a feed-forward network just by decomposing time into more layers. So I think ultimately feedback in cortex may have a lot to do with how many layers can you actually feed into into a system, the size of the head that it has to go through interesting places at some point, and there are sort of physical limitations to that, more than fundamental computational ones. At the heart of this is the question of how many recurrent computations you need, how much feedback you actually need, how many recurrent loops you need. If that involves only 2 or 3 loops, I think it's easy to convert that into a feed-forward network that will do the same job. If that involves 100 iterations and loops, it's harder to think about a biological system that will accomplish that. But at least at a very superficial level, I would imagine that
Can I ask
some of
just
these
a
same
focused
feedbacks
version of the same, a very focused version of the same question, or I try to, which is, what is the computational role of feedback in vision and audition? Like when we talk about feedback, maybe we mean something like top-down connections, like in the brain, or you know, or something like recurrent processing, like just from a computational point of view of the problem we're trying to solve, what do we think its roles are in each of the modes?
So I think that's the wrong kind of question to ask. If I ask you, what's the role of feed-forward connections?
Pattern recognition.
So, there's no role of feed-forward connection. There's a lot
on the
of
contrary, Tommy has a theory of it. You know, you have another theory. Something like very quickly trying to find invariant features. Trying to very quickly find invariant features of certain classes of patterns. That's a hypothesis. It's pretty well supported.
There's a lot of things that happen with feed-forward.
You want a feedback so that you can make things better somehow. I mean, you need a measure of goodness first. I mean, otherwise, I mean, how to build I agree with you that you can make a very deep structure which will function as a feedback thing, but always what worries me the most, and in general, a number of cognitive problems, how do I provide my machine with some mechanism which tells the machine that output is good or not? If the output is bad, if my image is making no sense, if there is no dog, but it's a kind of weird mix of green things and it's telling me it's a dog, I need a feedback. That's the point. I need a feedback, I believe. And I need to fix things. Josh is talking about tuning the cochlea. Yeah, that's of course, I mean, sharpening the tuning is possible. But in communication, I mean, if things are noisy, I go and close the door. That's a feedback to me. But I mean, I know as a human being, I know information is not getting through. And I do something about it. And this is what we badly
You just
need.
gave two good examples of, I think, just to generalize those, right? Or just to say them in more general terms. One role of feedback that people have hypothesized is like in the context of something like analysis by synthesis. If you have a high-level model of what's going on and you want to see, does that really make sense? Does that really explain my low-level data? Let me try it out and see that. Okay. Another is, yeah, like basically saying the role of the feed-forward connections is a kind of invariant pattern recognizer, and tuning those, tuning the filters, tuning the patterns to context, or in particular in a contextual way to make the features more diagnostic in this particular context. Right? Those are two ideas. And there are probably others. Yeah,
you gave the wonderful example with analysis by synthesis, or whatever. But even there, I mean, we need an error measure. And I'm not saying that least mean square error between what I generate and what I see is the right one.
So you think feedback would help to tune the error measure?
Well, no. I think I see chicken and egg problem. I think I need the error measure first before I even start using the feedback. Because, feedback, we can talk about it, but I mean, if you want to implement it, you have to figure out what is the error measure. Or what is the criterion that I recognize my output is bad or not good enough. I mean, it always will be a little bit bad, right? I mean, not good enough, and I have to do something about it. Once I know it, I know what to do. I think, well, maybe not me, but my students, whatever. Yeah. This is one of the big problems which we are working on, actually, figuring out how can I tell that output from my neural net or something is good or bad. I mean, and so far I don't have any answer.
But I think it's neat that those two or three different kinds of things, they are totally parallel in Vision and Audition. They're all like they're useful for both engineering-wise, and people have long proposed them both in psychology and neuroscience.
Generally, I think there's a lot to be done in this area, I think, and the notion of adding sort of, I mean, a lot of what's been happening in convolutional networks is sort of tweaks and hacks here and there. If there are fundamental principles that come from studying recurrent connections and feedback from the auditory domain, from the visual domain, those are the sort of things that, as Dan was saying, could potentially sort of lead to major jumps in performance or in our conceptual understanding of what these networks are doing. I think very rich area of exploration, both in vision and the auditory world.
And just I wanted to ask Josh one more thing, like kind of the common constraints thing. Like you were kind of saying, like it seems like there would be common constraints, and there are probably consequences of those. And just what are some kind of specific consequences that you think would come out? Like how can we think about this? Like what, to the extent that there is kind of a shared system, like what does it mean?
Well, so again, I can only, as several of the other speakers said, only give my very, very personal, subjectively biased view. But I think the brain has a way to think about the physical world, to represent, to perceive the physical world, and it's really like a physics engine in your head. And that it's like analysis by synthesis, it's a familiar idea, probably best developed classically in speech, but in a way that's almost independent of sense modality. I think we have different sensory modalities, and they're all just different projections of an underlying physical representation of the world. I think that whether it's understanding simple kinds of events, I was trying to illustrate here, or many other kinds of things, I think basically at some point, one of the key outputs of all of these different sensory processing pipelines has to be a shared system that represents the world in 3 dimensions with physical objects that have physical reality, things like properties like mass, or surface properties that produce friction when it comes to motion, roughness, right? There's some way to think about the forces, whether the force that one object exerts on another, or the force that an object presents in resisting when I reach for it, either the rigidity that resists my grasp and that I use of it, the weight of the object that requires me to exert some way to do that. So I think there has to be a shared representation that bridges perception to action, and that it's a physical representation, and that it has to bridge, it's the same representation that's going to bridge the different sense modalities.
Yeah, but to make that oriented,
more what?
More brain meat oriented, I think that there's a version of that could be a constraint is so strong that you have to have a special brain area that's used as the clearinghouse for doing that common representation.
I'm certainly not saying that.
Okay, right. No, I didn't think you were, but that would be a concrete result. Another concrete result is effectively that the individual modality structures are constrained in such a way that they have an API that has access to information from the other modality, and so that message passing is efficient, among other things, right?
Yeah, although
and
I think it's not
other.
often not direct. I think some of it might be, but a lot of it is going to be, it's not like vision talking to audition, but each of them talking to physics. Some of it might be one talking to the other. But I think it's very hard for a lot of mid-level vision and mid-level on audition are hard to talk to each other.
Right, and a third possibility is that it's actually not really so much that there's no particular brain area, and they're not exactly talking to each other API directly. It's just that there is a common constraint in the world that forces them to have similar structure, or sort of a line structure for representing the things that are caused by the same underlying phenomenon. Yeah, and that's the weakest of the types of constraints that you might have, right? The first one is very strong.
Yeah,
right.
But it's not vague or contentless. So Nancy Camisher and Jason Fisher have a particular hypothesis. They've been doing some preliminary studies, kind of intuitive physics engine in the brain, and they could point to a network of brain areas, some premotor, some parietal. It's possible. Who knows? It's very early days, but this might be a candidate way into a view of brain systems that might be this physics engine.
Right, but what you're
also ventral stream area.
Be something like if you optimize a network set of parameters to do the joint physics prediction interaction task, you'll get a different result than if you sort of just did each modality separately, and that would be that new different thing would be a better match to the actual neural response patterns in interesting events.
I think that would be really cool to explore.
That's, I think, the concrete way it would cash out, and that certainly seems plausible.
And it might be, a lot of traditional things which are traditionally called association cortex, right? This is an old idea. I'm not enough of a neuroscientist to know, but a cartoon history is there were lots of parts of the brain that nobody could figure out what they were doing because they didn't respond in an obvious selective way to one particular sense. But lost them. It wasn't exactly obvious what the deficit was, and so they came to be called association cortex. That connects to the study of cross-modal association and association to semantics, and this idea of association. It's this thing you say when you don't really know what's going on, but it's quite possible that those big chunks of the brain calling association cortex are actually doing something like this. They're this convergence zone for a shared physical representation across different perceptual modalities and bridging to action planning. And a big open challenge is that we can have a very what feels to us like a deep debate that we can think of as the central problem in neuroscience of how do we combine whatever you want to call it, I don't know, generative and discriminative, or model-rich, model-based analysis by synthesis and pattern recognition systems. But actually we don't, there's a lot of brain that have to do with reward and goals. And again, I thought Laura's talk was a really good illustration of this. Understanding, perception is representing what's out there in the world, but that's clearly got to be influenced by your goal. And what is certainly a big problem is the relation between those. That it says something that most of us who are studying perception don't think we need to worry about that, but I think we should, particularly those of us, again, echoing what Laura said, if we're studying learning, we definitely, I think, need to think about that more than we do.
It may not be exactly related to what you were asking, but I don't know. I believe that we are carrying the model of the world in our brain, and we are constantly evaluating the fit of what we expect to what we are seeing. And as long as we are seeing what we or hearing what we expect, we don't work very hard, basically, because model is there. You know what I'm going to say. I'm not saying anything special. I look reasonable, and so on and so on. And the moment this model of the world is for some reason violated, that may be one way how to induce the feedback, because then suddenly I know I should do something about my perception, or I may just give up and say, or I become very, very interested. But I think this model of the world, the priors which we are carry with us, are extremely important and help us to move through the world. That's my feeling. We had this, in speech we have a somehow interesting situation that we can actually predict, say, we are interested in estimating probabilities of the speech sounds, but we can also predict them from the language model, because a language model is learned typically very differently from a lot of text and that sort of things. And so we had quite a bit of success in trying to determine if the word recognizer is working well or not by comparing what the recognizer expects and what the recognizer sees. And if, as long as these things go together well, it's fine. If there is a problem between these two, we have to start working.
I think physics is a source of beautiful math and ideas. And there probably is, I think it's an interesting thing to think about, maybe some low-level tuning of some low-level mechanisms in both sensory modalities might be well thought of that way, right? But I think it is dangerous to apply too much of the physicist approach to the system as a whole, this idea that, we're going to explain deep stuff about how the brain works as some kind of emergent phenomenon, something that just happened to work that way because of physics. This is an engineered system, right? Evolution, engineered brains. It's a very complicated, I mean, we have had a version of this discussion before, but I think it's something that a lot of us here are committed to. Maybe not all of us, but the way I see it is, this is a reverse engineering science. And the brain just an accident. It didn't just happen. There were lots of forces over many different time scales acting to shape it to have the function that it does. So if it is the case that there's some basic mechanisms, let's say maybe at the synaptic level, that could be described that way, it's not an accident. I would call that biology using the physics to solve a problem. And again, there's a long history of connecting free energy type approaches to various, elegant statistical inference frameworks. And it could be very sensible to say, yes, that at some level you could describe that low-level sensory adaptation is doing that kind of just physical resonance process, or non-equilibrium stat mech could describe that. But the reason why nature has basically put that physics interface in there is because it's actually a way to solve a certain kind of adaptive statistical inference problem.
All right, cool. Let's thank our panel.